We continue our discussion about various laser structures, and today we will discuss about single frequency lasers. Single frequency lasers refer to semiconductor lasers which oscillate in a single longitudinal mode and a single transverse mode. The basic idea of single frequency lasers is illustrated here. We have discussed this, but let me recall it, that normally Fabry-Perot laser diodes oscillate in several longitudinal modes, because you can see here that this is the gain curve here and this is the loss line, and those frequencies, the vertical lines represent the resonance frequencies allowed by the resonator, but only those frequencies here 1, 2, 3, these three frequencies have gain. At those frequencies gain is more than loss, loss line is here, horizontal line, gain is more than loss, and therefore only these three frequencies, these three resonance frequencies or these three longitudinal modes can oscillate in a laser. So, normally all longitudinal modes or all resonance frequencies allowed by the resonator for which gain is more than loss will oscillate, which means generally we have few modes oscillating in a semiconductor laser. If you can somehow increase the loss for all modes but one mode which you want to lace, then it is possible to choose only one longitudinal mode. So, the idea is here again, the gain curve is the same, the resonance frequencies are the same, but if you can have a loss profile where loss is more for all frequencies but for one here, then it is possible that only one of these longitudinal modes will oscillate. For example, we will see the mechanism of choosing single frequency lasers, but if you have a Fabry-Perot echelon, we will see, let me show the next diagram and then come back. So, this is the laser here, it is AR coated, anti-reflection coated here, and the light output from this end passes through this. So, this is the semiconductor laser, the basic device, current passes through the device and gain is provided by this medium, and there is a Fabry-Perot echelon, tilted echelon. We have discussed how the tilted echelon chooses a particular required frequency. So, this is a tilted echelon in the cavity. So, the cavity comprises of this mirror and the mirror at this end, the cleaved end at this end which is not anti-reflection coated, and this mirror which is usually 100% reflecting, that is the one which cavity. So, this is the cavity from here right up to this. So, this is the way light is going back and forth, but there is an echelon in between. Echelon permits only certain resonance frequencies to pass through. The transmission of this echelon, if I may use the board, if you see the transmission of the echelon, so this is frequency nu, then the transmission shows peaks like this, narrow peaks. So, what I have plotted is the transmission of the echelon. So, this is transmission and this is 1. So, 1 point transmittivity or transmission versus frequency. So, there are frequencies here nu q and nu q plus 1. This is of the resonator. So, let me put them as dot. This is of the echelon, not of the resonator. So, there are transmission peaks here, which means a frequency which is here will pass through the echelon as if the echelon is not there. So, this echelon here, that frequency will pass through as if the echelon is not there, which means for that frequency, for these resonance frequencies, this cavity is a low loss cavity, whereas for any other frequency the echelon transmission is very small, which means that it does not act as a good cavity, and this is the idea by which you choose. So, let me go back to the figure again. Here you see the echelon resonance frequencies are these are the echelon resonance frequencies. separated by a free spectral range which is large, because the free spectral range nu f, if you may recall, is given by C divided by 2n into L, where L is the length of the cavity. For the echelon, L is very small, and therefore the free spectral range or separation between the resonance frequencies is large. But for the laser cavity comprises of this whole cavity. Let me show again here. So, this is the laser cavity from here to here. This L is very large, and therefore the resonance frequencies permitted by this cavity are much closely placed, or the free spectral range for this whole laser cavity is much smaller, and therefore let me go back again to the other figure here. So, these vertical lines correspond to the laser cavity, and these vertical lines correspond to the resonance frequencies of the echelon. Whenever the echelon resonance frequency coincides with the laser cavity resonance frequency, that particular frequency will pass freely inside the cavity. That is, if this happens to be coinciding with the allowed resonant frequency of the laser cavity, then this frequency transmission is 1, which means it does not see the echelon at all. It is low loss. Echelon is a low loss device for this frequency. Inside the cavity there is an echelon which is a high loss device for any frequency which is here, because it is not allowing those frequencies to pass through. So, what happens to those frequencies? Those frequencies which are incident here will get reflected in this direction. It is a tilted echelon. The tilted echelon, the tilt has two reasons. Why do we need a tilted echelon? One, the frequencies which are not transmitting will get reflected, and when it gets reflected, it will go like this at an angle. So, it does not go back. The second reason why you use a tilted echelon is by changing this angle theta, you can change the separation nu f. So, nu f is this frequency separation nu f. So, this frequency separation can be tuned so that at least one resonance frequency coincides with the resonance frequency of the laser cavity. So, at least one resonance frequency, this one or this one, coincides with the laser resonance here. So, that particular frequency loss is very low. For all other frequencies here, the loss is very high. So, this frequency here sees a low loss, because that is the transmission resonance of the echelon. So, this is the principle by which it is the same laser structure, but the cavity is now lossy for all frequencies but for one. Therefore, only the loss curve here dip for one particular frequency, and which means it is here for this frequency. So, loss is low. So, gain is higher than the loss, and therefore, this is the frequency which will oscillate in this laser. By this means, we have chosen one single longitudinal mode. The laser structure here, this is an external cavity laser. So, external cavity laser, which means this is the cavity which is coupled to the laser, and therefore, by using this echelon, you can force the laser to oscillate only in one frequency corresponding to the resonance of the echelon. So, this is one of the widely used technique called external cavity laser, ECL, external cavity laser. Oh, it is written already, external cavity laser. There are other means by which you can single frequency. The second one which is shown here is a grating. So, there is no cavity here. So, this is anti-reflection coated. Here is this end is the cleaved end, which has 32% reflectivity. So, light which is going back and forth, this is a rotating grating. By rotating the grating, you can make only one wavelength which is reflected back. You see, this is a grating. So, if you have a spectrum, as you know, for the grating you have d sin theta equal to n lambda. So, different lambdas will have different theta. It is a reflection grating. There are transmission type of gratings and reflection type of gratings. So, this is a reflection grating. In a reflection grating, so different wavelengths correspond to different theta. In general, a theta could get reflected like this, which means it will not go back to this, but only one particular incident angle will go back into this, and therefore, only one wavelength will satisfy this condition of going back. So, by rotating the grating, you can choose different wavelengths to lace in this cavity, or at a given angle there is only one wavelength. Please see, if you see the gain curve, so this is lambda or frequency whatever, the gain curve is like this. If you choose the grating so that at 1 lambda theta is such that light goes back, so it could be here for example. So, for that loss will be very low. Principle is the same. For all other wavelengths, loss will be very high. So, this is loss line, this is the gain curve. One wavelength lambda here which satisfies this condition, where the wavelength is reflected back into the cavity, will have very low loss. For all other wavelengths, the light which is reflected here, those wavelengths which are reflected are at an angle, so they do not go back exactly here. They may hit here, they may hit here, or they may just go out. So, there is no feedback. It is highly lossy cavity for other wavelengths. So, this is the way that you can choose any particular wavelength and force the laser to oscillate in a single longitudinal mode. This is also the principle for tunable lasers, external cavity lasers. There are tunable lasers which are based on external cavity structure. You can tune 50 nanometers. The lasing wavelengths can be tuned of the order of 50 nanometers by using external cavity lasers, where you use a rotating grating here. The grating is rotated by piezo controls by current. It is not manually rotated. It is with high precision you can control the feedback, and therefore, the wavelength which you want to choose, one can use the stepper motors here to rotate this, and you can choose the wavelengths in steps, or you can continuously choose the wavelengths which you want to lace. In other words, what you are doing by rotating the grating is, now this is the curve for a particular angle. At a later angle, so let me draw this with the dotted line, the curve could be like this. Which means at a later position, at a different position, this is the lambda for which, so this is the lambda dash, this is lambda for which initially there was low loss, but by rotating I have shifted the curve. The wavelength for which you have low loss is this one, and therefore, only this wavelength will lace. This is the principle of external cavity tunable lasers based on external cavity rotating grating. The grating condition is given here. This is actually 2d sin theta equal to n lambda. I am sorry, this is 2d sin theta equal to n lambda. So, d is replaced by the period here, grating period 2d sin theta equal to n lambda. N is order 1, therefore, n is not written. For the first order, it is n equal to 1, first order. One can use higher orders also. So, let me go to the extension of this external rotating grating. What the grating was doing is, one particular wavelength had high reflection going back into the cavity. So, here is a structure which is called the distributed feedback laser. First of all, the feedback is distributed all along the length, that is why the name distributed feedback laser. Please see the laser structure. The two ends are anti-reflection coated, AR coated. The two ends are anti-reflection coated, which means there is no cavity as such. However, this structure supports a guided mode here, like all other double heterostructure lasers, it supports a guided mode. In the case of a distributed feedback structure, there is a grating which is a corrugated grating, a periodic structure in the cladding here. The mode which is propagating in this direction continuously sees reflections at these corrugations by this periodic structure. The mode which is going in this direction gets reflected continuously, and therefore, the feedback is distributed all along the length, hence the name distributed feedback laser. Let me explain this a little bit more on the board. Distributed feedback lasers. These are of course fixed frequency lasers, not like external rotating grating lasers. You can tune them, you can rotate the grating and make different angles correspond to different wavelengths which get highly reflected. But in the case of distributed feedback lasers, they are fixed wavelength lasers with a little bit of tunability possible. So, let me draw it on the board here. So, I have drawn only, so these are the, okay, let me show the cladding layers also. So, this is the active layer and there is a mode which is traveling, because this is a waveguide. Recall that this is high band gap region, which means low index and high index. So, this forms an optical waveguide. So, it supports a mode which goes back and forth. If you perturb this mode is, let me show it like this. Many of you have studied fiber Bragg gratings, where there is a grating which is in the core of the fiber, So, if you have a periodic structure, let us say there is a periodic refractive index variation in this direction. So, this is a periodic refractive index variation. There is a guided mode which is propagating, but it encounters a periodic refractive index variation. So, n high, n low, a modulated n high, n low. It is having a periodic reflection. So, the mode is undergoing periodic reflection at the interfaces like this. The mode is continuously undergoing periodic reflections as it travels in this direction, which means it is getting reflected at interfaces continuously. For simplicity, I will show this as a step variation. So, let me show the refractive index variation like this, step variation. And here is the light mode or plane wave. You can look at plane wave also going like this. It is the same principle as interference filters, high reflecting coatings, multi-interference, multi-layered coatings, it is the same principle. So, if the wave is propagating like this, so this is n high, this is n low, n high, n low. What I have plotted is refractive index n versus x, if x is the propagation direction z. So, let me put z, n of z. Okay. So, high index, low index, high index, low index and so on. So, if you see plane waves, ray, you look at the ray picture for simplicity. A ray is reflected from here at this interface, this propagates here and this also gets reflected here. The reflected wave comes back and both of them join here. Now, the ray will get resonantly reflected, the wave will get resonantly reflected if, let me call this as lambda, wavelength lambda, and this is half the wavelength, lambda by 2. So, this ray or this wave which gets reflected and comes back, if it adds in phase with the wave which is reflected here, then there will be coherent addition and you get reflection, high reflection for those wavelengths, which means the wave k0 into n refractive index into the thickness lambda by 2 round trip, therefore 2 times lambda by 2. Please see, this is the path length and phase difference of the wave between this and the one which has been reflected from here is this much. So, this is delta phi. But you remember that if this is high index, this is low index, there is an additional phase change of pi here, but there is no phase change of pi here. And therefore, if this difference happens to be an integral multiple of pi, that is odd integral, or if I take the first order, then if this is equal to pi, then I will have a resonant reflection. Please see, the wave which is coming back from here will add in phase with the wave which is reflected here if this condition is satisfied. 2 times round trip phase, that is why 2 times phase constant into refractive index of the medium into the distance equal to pi, that is del phi. So, what does this give you? This gives you that this goes off and we have 2 pi here, 1 pi goes there, and therefore, this is 2 pi by, okay, let me write 2 pi by lambda b into n into lambda equal to pi, or lambda b is that wavelength. So, lambda b is equal to 2 times n into lambda. If you take a period lambda and the refractive index of the medium n, then this wavelength will get resonantly reflected. No other wavelength will get added in phase, so they will get transmitted. So, if you see the reflection spectrum of such a structure, you will see that there are side lobes because of Fourier components of the step like variation. So, this will be the wavelength lambda b. So, what I have plotted here is reflection r versus wavelength lambda. This is the basic idea behind operation of a Bragg grating. It is the same which you see in fiber Bragg gratings also, where the grating is returned right into the core. In the case of a semiconductor lasers, you could have written grating in the core, but you do not try to write a grating in the core, because any fabrication step which introduces some variation here will also introduce defects in the active region, and the active region or generation of light is highly sensitive to defects. We always wanted defect density to be as minimum as possible, otherwise non-radiative recombinations will take place and the light generation will go down. And therefore, instead of writing across the whole waveguide, they make corrugations or periodic refractive index variation in the cladding. That is why you see that structure which you saw on the PPT there, that you have periodic refractive index variation here, because the materials are different. Please see, this material is different, this material is different here, and therefore, the refractive index here is different, refractive index here is different. And the mode here, please see, this is the mode, guided mode. The tail of the mode sees this periodic structure. If any part of the mode is perturbed, mode is one field distribution. If you perturb it anywhere, the whole field distribution will get perturbed. It is not that even if the tail sees this periodic structure, the entire field will see the periodic structure. And therefore, the periodic reflection which takes place from here is seen by the entire mode. In other words, as the mode propagates, there is continuous reflection which is coming like this, backward reflection, as the mode is propagating. Because what I have shown here is the material structure, but if you see the refractive index variation, that will also be the same. The refractive index here is different, n high, this is n low, n low, n high. This is what you see. And what is this? The tail of the mode. So, this is the mode. I have zoomed the same structure a little bit more like this. and you see the periodic, the tail of the mode or the evanescent field here sees this periodic structure as it propagates, and it continuously suffers reflection. Why it is suffering reflection? Because it sees interfaces. The condition in this case is that the reflected, the phase difference between identical phase points here, this is one wavelength, this is a phase grating. A grating is a structure where there is either refractive index variation or transmission variation. The normal gratings that we see are called amplitude gratings. You are familiar with the gratings where you make corrugations by a diamond edged blade, and then you have a grating structure. So, what do you get? You get a structure where there is opaque, there is transmitting, opaque, transmitting. So, this is opaque where you have scribed it, this is transmitting, this is opaque, this is transmitting, this is opaque. This is the normal diffraction grating that we are familiar in light experiments. It is opaque, transmitting, opaque, transmitting. Means what? There is no transmission from here, but there is full transmission from here. And this is the diffraction grating, but this is the amplitude grating. Whereas here, this is called a phase grating. There is no opaque or transmission, but the refractive indices are different, and these are called phase gratings. So, a distributed feedback laser has a phase grating in the cladding region. 2 points. Why in the cladding? Because the fabrication process should not introduce defects. If there are defects in the active region here core, it will be detrimental to the performance of the source. Therefore, it is corrugated in the cladding. Second, the periodic structure gives continuous feedback all along the length. There is no reflection from these ends are anti-reflection coated, so that there is no reflection coming from here. Reflection is only by these. But this being a periodic structure, the reflection is wavelength selective. The reflection is wavelength selective, which means only one particular wavelength which satisfies the Bragg condition, this is the Bragg condition, will get resonantly reflected as the mode goes in this direction. Similarly, when the mode comes back in this, you see it is continuously getting reflected, means it is generating the backward propagating mode. The backward propagating mode, as it continuously propagates in this direction, this is the backward propagating mode, it gets continuously reflected like this, in this direction. So, when the mode is coming in this direction, it is continuously getting reflected to the other side, whereas when it is traveling from this side, it is continuously getting reflected. But the reflection is not at the ends, but distributed all along the length. Hence the name distributed feedback. Reflection is a feedback in the case of lasers, and reflection is distributed all along the length. Hence the name distributed feedback lasers. So, in a periodic structure, the condition is written like this. So, these are the two phase points, identical phase points, and this is lambda. So, you can show that 2 times k naught into n effective. Now, n effective because effective index of the mode is k naught into n effective. It is not a plane wave. A plane wave, if there is a refractive index n and a plane wave is traveling like this, then its k will be equal to k0 free space wave number multiplied by refractive index. But a mode is characterized by a propagation constant beta, which is equal to k0 into n effective, effective index of the mode, which lies between the refractive index of this medium and this medium. All right. So, this into lambda will be equal to q times 2 pi. This is the resonance condition, where q is the order. If you are taking first order grating, then q is equal to 1. equal to 1 for first order grating. If you simplify this, how did I write this? That the round trip phase within one period is an integral multiple of 2 pi. General condition for resonance, round trip phase is an integral multiple of 2. Round trip phase is twice wavelength into phase constant, k0 into n effect. This is k, phase constant, multiplied by the distance in one round trip, 2 lambda, must be equal to integral multiple of 2 pi. There is nothing to remember. This is just the concepts are remembered, and you get that lambda here is equal to lambda 0 divided by 2 n. So, this is the Bragg wavelength. Only if you choose a period lambda for the corrugation here, only this wavelength will suffer maximum reflection, and therefore, the loss will be much less for that. All other wavelengths will simply get transmitted out. These ends are anti-reflection coated, so there is no reflection coming back. All other wavelengths will simply go out, which means there is no feedback. Feedback is for only this wavelength. What kind of numbers that we have, what kind of period that you have. So, if you substitute some number, let us say in optical communication, you want to use at 1.55. So, let us say lambda 0 that you want laser to oscillate at 1.55. You want to make a source distributed feedback for 1.55 micrometer, then you will have to use lambda is equal to 1.55 divided by 2 n effective. N effective is approximately 3.5. Why 3.5? Because the active medium may be 3.6, outside medium may be 3.4. These are typical numbers for semiconductors. Refractive index is 3.5, and therefore, n effective I have chosen as 3.5. So, this is, how much will this be? Approximately 0.23. So, that is the period that is required, the corrugation that is required to be made in the cladding. This is a distributed feedback laser, which is all these conditions are here in the slide. You can see k naught into n effective into 2 lambda is equal to q times 2 pi. Q is equal to 1 for first order grating. These are all given in the slide. N effective is the effective index of the mode. So, all communication sources used for optical communication are distributed feedback lasers. Why we use distributed feedback lasers? Because we want a narrow line width for the laser. As we discussed in the last class, if you use a narrow line width source, the dispersion will be much less, and therefore, you need a narrow line width source or a single frequency laser. So, the distributed feedback laser is a single frequency laser. There are some intricacies here, more details and related to distributed feedback laser. I have talked about the basic principle. Actually, although this is the wavelength that I have written, when you make a distributed feedback laser, if it is perfectly symmetric, then it will oscillate in 2 modes which are adjacent, and there are techniques to suppress such modes. If you see the actual spectrum of a distributed feedback laser, if you see this is nu versus distributed, then if this was nu b, this is nu b, the Bragg frequency corresponding to lambda b. So, lambda b. So, lambda b is equal to 2 times n effective into lambda. So, nu b is C by lambda. So, nu b here is equal to C divided by twice n effective into lambda. This is the Bragg wavelength, but actually you see that there are two modes. If you see a practical structure and which has some more side modes here, side lobes, and there is an important parameter we will discuss. I will not go into the details of this, but this is slightly shifted. The frequency nu of the laser is given by nu b plus minus half q plus half into the free spectral range. The free spectral range is C by 2 n effective into L here into q plus half. Let us say q is equal to 1. If q is equal to 0, it is the central one here. So, the 0th q equal to 0 will have two values plus or minus. So, you will have two modes instead of one at nu b. This is the value corresponding to nu b. Please see this. We thought that by taking a grating we will get one particular frequency nu b, but actually because of the coupling between the forward propagating wave and the backward propagating wave, a coupled mode analysis will show you that it will support two modes. The modes are given by this expression, which means even if you put q equal to 0, then you have nu b plus minus half times this. So, this is the expression for the, which means there are further modes which are separated like this. This can be explained only by coupled mode theory, but it is possible to suppress this and make the laser to oscillate in the central mode, and of course, the side lobes will always be there. Side lobes are there because the structure is not perfectly sinusoidal. So, you will always get side lobes. In a perfectly sinusoidal structure, the Fourier component will be at one frequency. But if you take a step or if you take any other, you always get the Fourier components at the harmonic frequencies, and therefore, that is why you get the side lobes. And there is a parameter. Normally, these lasers oscillate like this. These are called side modes. This is the required mode. So, what I have plotted is the power, let us say I of nu or I of lambda versus nu frequency. The laser output, if you see, I said that these are single frequency lasers, it is oscillating in one frequency, but actual practical devices will always have side modes coming here. But the power in these is much smaller compared to the power here. The power here is typically 30 dB down. 30 dB means 1000 times smaller compared to the central lobe, typically. And this is characterized by a parameter we have, I think I have shown here, single mode, side mode suppression ratio. So, these are the side modes, side mode suppression ratio. When you buy a DFB laser, there is always this specification will be given, side mode suppression ratio. So, side mode suppression ratio or SMSR refers to the difference in power here in dB between the required central mode, that particular frequency, and unwanted side modes, which come because of the periodic nature of the grating. So, this is a parameter typically 25, 30 dB or better, SMSR. All right, let me go back to the DFB laser here. So, this is the structure and here is the spectrum. just to illustrate, if you take a Fabry-Perot laser, is the same laser, you have the laser oscillating in multi-longitudinal modes, and if you have a periodic grating here in the cladding to make it a distributed feedback laser, it oscillates in a single longitudinal mode. Normally, if you keep the linear scale, you will not see this. If you keep it, this is 30 dB, 1000 times smaller. Only if you keep log scale, you will see this. In the spectrum analyzer, if you choose the log scale, then only you will be able to see this. Otherwise, the power here is 1000 times smaller. So, in a linear scale, it will be just not there. That is why here I have not shown any of this. Actually, there is a small amount. This is an illustration showing that it picks up one single longitudinal mode. So, DFB laser is a single frequency laser. All right. We go to the extension, that is distributed Bragg reflector lasers. This is not distributed feedback, but distributed Bragg reflector. What is the difference here? You can see the structure, that there is a difference in the structure between DFB and DBR. I will not go into the details of this coupled mode analysis, but those of you who are interested, you can see the references. Recall the Fabry-Perot laser. The Fabry-Perot laser has reflection coming from here, from the two ends, the Fabry-Perot. So, these are the cleaved facets, and therefore, there is, because it is a cleaved facet, it is normally not frequency sensitive. Almost all frequencies will get reflected, because it is a mirror basically. But instead of this broadband mirror means mirror which has a wide reflectivity over a wide frequency range. If you use a frequency selective mirror here, like the interference filters, if you put a frequency selective mirror or high reflection coatings, for example, here if you put a periodic structure n high, n low, n high, n low, and make a high reflection coating here, then that coating will be frequency selective. It will be highly reflecting only at one particular wavelength. So, this is a possibility, but in practice it is not a practical solution in the considering the fabrication process. So, instead of this, if you have the Bragg reflectors, so this is the structure here. If you have the periodic reflector which we had all along the length in the case of DFB, only at the ends, we do not have anything here, and here again we have the periodic structure. So, the mode is travelling like this, back and forth. At the ends, there is a frequency selective grating here. It is not a separate bulk layer, but it is within this. This can be much easily fabricated by lithography. This is not by lithography, you have to, it is easy to show here, but in a practical situation, taking the wafer like this and depositing interference layers is very cumbersome process, and therefore, this is monolithic process, that is on the surface you can do this lithography and epitaxy. That is etching and regrowth, both are required, but it is a much easier solution. So, what you have is the reflector is a Bragg reflector here. In this section we have Bragg reflector. Bragg means periodic immediately. So, there is a periodic structure which is providing reflection, and that periodic structure is wavelength selective, and therefore, you have distributed Bragg reflector. So, these are the Bragg reflectors. At the two ends, and the gain medium, the gain providing contact electrode is only here. the current is flowing through this region, current is not flowing through this region. This is the structure of DBR laser. What are the advantages over DFB? A DBR laser is much more stable in frequency. I am making a statement that a DBR laser is much more stable in frequency of the output. In the case of a DFB laser, all right, let me go back to the DFB here, DFB. You see that the metal contact is here, carriers are flowing across, carriers are also flowing through the grating region, carriers are flowing through the grating region which is selecting the frequency. We have an expression that lambda b here, that is the frequency of which is selected, is equal to twice n effective into lambda. Lambda is fixed because once you have fabricated the corrugation, that is it, lambda is fixed. However, the refractive index of the medium here is a function of the current which is flowing through. When carriers are injected, the medium has gain or loss depending on injection of the current. Depending on injection of current, we can make either EFC minus EFV greater than EG or less than EG. If it is greater than EG, then only we have gain. So, what determines? The injection current determines whether there is gain or not. Refractive index of a medium in general is given by NR minus I times Ni. Refractive index of a medium in general is complex, and because it is the complex part which will tell you whether the medium is absorbing or amplifying. If Ni is greater than 0, here this means it is absorbing. If Ni is less than 0, it is amplifying. This is basic optics. I hope you understand that a wave psi can be written as if you are taking a plane wave, e to the power of I kx, that is I k z, if it is propagating in the z direction, into I omega t kz minus omega t, or omega t minus kz, whatever way that you want. So, you see that k here is k0, k here is k0 into refractive index n, which is equal to k0 into this refractive index is a real part minus I times Ni part, and therefore, you have minus this term here. So, if you look at this term, you get e to the power I k0 nr into e to the power the second part, that is minus I square. So, minus minus is plus. Oh, let me write this the other way, because normally in optical waveguides in quantum mechanics we write this way, but in optical waveguide we write I omega t minus kz. So, k into z, and this is here, and so the first part is minus I k n0 into r, this is an oscillatory part. The second one will be minus I into minus I, so minus minus plus, and I square is minus 1. So, you have minus k0 into Ni, k0 into Ni into z. What I have written is an expression for plane wave. This is a plane wave, propagating plane wave in the z direction. Okay. Psi is equal to amplitude into this. If the refractive index is complex, so k is k0 into n, refractive index is complex, I have substituted here the complex quantity, then I just substituted back, I omega t I have left, you can keep I omega t. So, a into e to the power of I omega t here. So, you see that there is a term which is coming like this is exponentially decaying, these are oscillatory. So, if you want to see the intensity which is equal to mod psi square which is equal to a square into these two terms are gone and you have e to the power minus 2 k 0 n I into z. So, what does that mean? The intensity is decaying with z, the power is decaying with z, that means if Ni is positive then this is absorbing with z, the medium is absorbing. Are you able to follow that this is z here, therefore, as z increases this quantity is exponential e to the power of minus something which means 1 by e to the power. So, it is greater than 1 in the denominator. So, this quantity drops down continuously. This a square I can write as I 0. So, I have I of z is equal to I 0 into e to the power minus 2 k 0 n I into z. The intensity is continuously decreasing with z if Ni is greater than 0, that is what I have written here. Ni is greater than 0 means the medium is absorbing. If Ni is less than 0, if you substitute Ni as negative, negative becomes positive, so it is amplifying, medium is amplifying. When you pass a current here, the refractive index is this. When you pass a current, Ni decreases and it goes from 0 greater than 0 to less than 0, and that corresponds to gain. By passing an injection current and maintaining the gain in the medium means Ni has become less than 0. The medium is complex in general and amplifying and absorbing media are complex in general, have a complex refractive index. Normally, we do not consider this because we treat media which are transparent. If you take glass and do all the optics, then you consider that the glass is transparent. You are not considering absorption. That is why you never use this part. Transparent means this is equal to 0. Ni equal to 0 is transparent. So, we only talk about the real part of the refractive index in normal optics. But if the medium is absorbing or amplifying, it means the refractive index is complex. So, we come to the point here, as you pass current, Ni changes in the medium, Ni goes from positive to negative, that is the medium becomes absorbing, then transparent at transparency carrier density, and then it becomes amplifying, which means Ni is changing. Through Kramer's-Kronig relation, some of you may not be knowing, but Kramer's-Kronig relation, it relates the relative imaginary part to the real part of the refractive index, Kramer's-Kronig relation. This is true for any real, that is any complex quantity of a real system, that the imaginary part of the complex number is related to the real part of the complex number. So, if this changes, NR, if this changes through this relation, they are linked through this relation. If this changes, the frequency changes, because you see this was the real refractive index. So, this changes if the real part of the refractive index changes, the frequency changes, and therefore, depending on the current here, if you have a larger current or smaller current, the frequency of the light gets shifted. In the case of a DFB laser, where in the case of a DFB laser here, this is the DFB laser, the current is passing through the grating which is selecting the frequency. Because the refractive index of the medium here changes due to injection current, the frequency also changes with injection current in a DFB. In a DBR, here is the DBR structure, the current is passing through the active medium where there is no frequency selection. Frequency selection is done at the ends, and therefore, that is not affected. the refractive index here is not affected because the carriers are moving here, and therefore, the frequency remains stable. Irrespective of the current, the frequency remains stable. This is the main advantage of a DBR laser over a DFB laser. However, it is a little bit more difficult to fabricate this at the ends, and normally unless you really require an application, unless you really have an application where you require extreme high stability of the laser frequency, tend to use DFB lasers. Therefore, in communication we normally use DFB lasers because we use the current system at least uses the on off keying or intensity modulation scheme, and therefore, it is not an issue. However, if you use coherent systems, then this will become an issue. The frequency shift will be an issue. Okay. We will stop. It's time here. So, we will stop here and continue in the next class.